Okay, let's see how we can use Colab to realize our two-opt algorithm. So first, we generate 10 points on a 10 by 10 2D space as our cities. So here for convenience, we generate a random permutation of all the cities to get a feasible TSP tour. So for example, here we have a realized permutation, which is city 2 to city 8, blah, 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 until city 5, and then finally go back to city 2. So here we wrap up the calculation of TSP cost and then plot of TSP tour in functions. So for example, here, when we have the sequence of cities we visit, we will calculate the total cost based on each adjacent pairs of two cities. So for example, the first city is 2, the second city is 8. So our first distance or the cost will be C28. And then the second is from city 8 to city 4. And then the next distance will be C84, blah, 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 until finally we reach the last city, which is city 5. Then we have city, the cost is 0 to 5. Because finally we need to go back, so we will add city 5 to finish the TSP tour. So to achieve this, we will first extend the sequence of city with its starting point as 2. So that means we have this 5 as the original sequence. We will extend this with our starting point as extended list to indicate this is a loop. Similarly, we can plot it, and then for each edge, each distance from two adjacent cities, we will plot locations in the figure. So for example, here you can see this is a random realized TSP tour. So definitely this is not optimal. We can see the choices are very zigzag. And then we will see how can we use two-opt algorithm to dramatically improve it. So here is a function which we calculate one swap. That is the one step for the opt2 algorithm. This is the one step for this two-opt algorithm. So that means we have 4 points. In this particular case, we have I plus 1, and then to j, and then j plus 1. So the I value and j value are enumerated from all possible cases. And then when we enumerate all these cases, we can calculate this distance from ci to ci plus 1, from ci to I plus 1, the distance from I to I plus 1, and then in the middle is the path, and then we have the distance from j to j plus 1. This is our total, this is our benchmark before the swap. And then after we do the swap, we will have the swap of j and I plus 1, and then have j plus 1, which keeps the same. So after we do this swap, we will have the new distance to compare with is from I to j, and then plus the distance from I plus 1 to j plus 1. So we compare these two distance terms before and after the swap. And then if we find out that the distance after the swap is smaller, then we can do the update of the sequence. So update of the sequence is also very simple. Previously it's from I to I plus 1, and then after several intermediate nodes we go to j, and then j plus 1, and then go back to I. So after this switch, we will keep the route from j plus 1 to I, but we kind of reverse the path back from I to j, j minus 1, j minus 2, blah 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 until I plus 2 and I plus 1. So this is totally reverse of all this sequence. So we implement this with our very simple swap operations. Remember that we do this swap based on each pair. So first we will swap the node I plus 1 and j, and then we will swap I plus 2 and then j minus 1, blah 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 until in the middle we swap two adjacent nodes. Let's see, k plus 1, which in the middle. After we swap them, we finish the entire reverse operation of the sequence. So after we finish this, we can provide a new update. We can provide an update on the new sequence and then return it. So if we couldn't find any swapping operations that improve the total distance, so that means this condition cannot be satisfied, and finally we will return a label 0 to tell us that we cannot find one feasible solution that improves during our 2-opt algorithm. So in short, if we can find an improvement, we will return 1 with the new update of sequence. Otherwise, we will return 0 to indicate we cannot find a good update, and then return the previous sequence. So here we will show how we can do this update step by step. We will print out if the swap is improving the distance or not. So here we have already done one swap. So here we can see the label is 1, so we find one swap which is good. And then the cost after we do the swap is given here. And then this is a new sequence after the swap. And if we keep running this, So we can see we find another update which is a little bit less than previous cost. And from the figure, you can also see it's a little bit better with the new sequence. Let's keep doing this. We have another swap, another swap, another swap, another swap, another swap, another swap, another swap. So after we see the label now becomes 0, that indicates we cannot find any 2-opt swap operations to improve the distance. So this makes sense. From the current result, you can see that the path is already neater. And then from our intuition, probably it's hard to find any improvement directly. And then the TSP distance are dramatically reduced almost to its half. Now it's around 20 something. And here we have the final sequence. So after we have this one-step TSP tool or improvement use 2-opt algorithm, we can create an iterative method. Keep using this one-step improvement to achieve a very good solution, which is our greedy algorithm. So here we can see that after we do our greedy search, it takes us about 9 swaps, and then the total TSP distance is from around 42 and then gradually reduced to 28, 26, 27 here. This is 27.69.